So horizontal asymptotes are another common but not guaranteed characteristic of rational functions. Many have them, some do not. So the rule comes down to comparing the degree of the numerator and denominator. And the reason for that is that we're talking about long-term behavior. We're talking about what's going on way, way at the very far right and way, way at the very far left as x gets very, very big in either direction. So we've already seen this kind of set up from dealing with polynomials, and we used what was called the lead coefficient test, or as I prefer to call it, the lead term test. That is to say, it is the lead term, the coefficient and highest power of the polynomial that determine the end behavior of its graph. So it's going to be the same thing for rational functions, and the idea is that we can figure out what's going on simply by looking at the degree of the numerator and denominator. So in keeping with n for numerator and d for denominator, I used capital letters for the functions and lowercase letters to talk about their degrees. And the rule was that there were three ways this could turn out. That the degree of the numerator was less than the degree of the denominator, that they were equal to each other, and that the degree of the numerator was greater than the degree of the denominator. In the case that the degree of the numerator was smaller, the horizontal asymptote was at y equals 0. In the case where the degrees were the same, the horizontal asymptote was at, well, it looks more confusing than it is, y equals a sub n over b sub d. But really, this was just the lead coefficient of the numerator and the lead coefficient of the denominator. So you literally just take the two lead coefficients and keep them, and everything else just kind of disappears. And in this case, there is no horizontal asymptote. So, perhaps a bit of a demonstration as to why these work the way they work. We'll look at a few examples, one of each of them, and attempt to show why it is that they come out in this particular way. So, first we'll tackle the degree of the top being smaller than the degree of the bottom. So, let's use f of x is equal to 2x plus 7 over x cubed minus 9x plus 13. The entire idea here is that as x approaches either positive or negative infinity, the numerator approaches its lead term. Whatever 2x does, that's what the numerator is going to be doing. As far as getting larger or smaller, and the denominator is a polynomial, so it does what its largest term does. Taken together, we can say that the rational function, which is the fraction of these two polynomials, would then approach 2x in the numerator and x cubed in the denominator. So really what we're saying is, and it's, kind of a long mathy way of saying that the bigger x gets, the more this matters and the less that matters. Because, well, 7's always going to be 7. It's never going to get any bigger or smaller than that. But the bigger x gets, the bigger this term will get. We see the same thing in the denominator, where 13 is always 13. Now, 9x, the negative 9x will get big the bigger x gets, but this is going to way overpower it. X cubed is way bigger than 9x for large values of x. Let me put it this way. If x is 10, 10 times 9 is 90. If x is 10, 10 cubed is 1,000. And that's only at x equals 10. If we use much larger x values, that difference becomes considerably more pronounced. So what it comes down to is that as x approaches positive or negative infinity, the function approaches the ratio of its lead terms. Of course, we can't stop there because we do run into a bit of a problem. I mean, the bigger x gets, the bigger both of these get. So where does that leave us? Well, the advantage here is that by kind of getting to ignore the other terms, we make this a lot easier to look at and deal with, to the point where it's now a monomial over a monomial, and we can simplify it. Specifically, we can simplify one factor of x in the top with one factor of x in the bottom, and it goes to 2 over x squared. Well, here's the fun part. Now that we've simplified it like that, the bigger x gets, 2 remains 2, and it will always be 2. But the denominator is x squared. And that's going to keep getting bigger and bigger. So for example, when x is 10, ten squared is 100, and we get 2 over 100. When x is 1,000, we get 2 over 1,000 squared, which is 2 over 1,000,000. A teeny, teeny, tiny little value. And we're not even at that big of an x value yet. The further we go, the bigger the x value we use, the bigger this denominator is going to get, and the top will always stay just a lowly little 2. Now, how does this translate into the n is less than d thing? Well, first of all, the degree of the numerator is 1, and the degree of the denominator is 3, so we fit. The degree of the top is smaller, but the key is in what happened here. If we isolate down to the lead terms and simplify x's like this, a higher degree in the bottom means that that's where the leftover x's are going to be. All of the x's will disappear out of the top, some out of the bottom, and there will be extras in the bottom. And we will have exactly this situation: a constant in the top, a power of x in the denominator. And that will always go to 0 as x goes to positive or negative infinity. Let's next take a look, keeping that in mind, let's next take a look at a function where the degree of the numerator and the degree of the denominator are the same. This time, let's use 12x cubed plus 8x squared minus 25x plus 18 all over 2x cubed minus 14x plus 5. You know, for all that writing though, again, the top is just a polynomial. So the bigger x gets, the numerator is going to do what 12x cubed does. And the denominator is a polynomial. So the bigger it gets, or the bigger x gets, the denominator will do what its lead term does, 2x cubed. And we end up in a similar situation to before, where we can now say that the rational function as a whole is going to approach its lead term of the numerator over its lead term of the denominator. Now, This is where it becomes important looking at the degree of the top and bottom. And this is where the distinction comes between what we saw in the previous example and what we see here. Namely that, since we're down to a single term, top and bottom, we can do some simplifying. And in this case, since it is the same power, top and bottom, all of the x's cancel out exactly, leaving us with just the lead coefficient of the top and bottom, which can then be simplified. Not in all cases, but in this one, yes. And that is where our horizontal asymptote is going to be, at y equals 6. So again, it has to do with the degree of the top and bottom because it has to do with how the powers of x are going to simplify at this step. So, with that in mind, it shouldn't be too much of a leap to move on and look at what happens when n is bigger than d. And hopefully, already have an idea of what we're going to see. This time, our function will be 5x squared minus 9x minus 30 over 3x plus 6. And what we have here is that the numerator is larger than the denominator. The degree, rather, of the numerator is larger than the degree of the denominator. So again, we get that as x approaches positive or negative infinity, the numerator will do what its lead term does, and the denominator will do what its lead term does. And put together, we have 5x squared over 3x. So once again, we reach that point where now we can simplify the factors of x. This time, however, it's the top that has more factors of x. So it's the top that is going to have the leftover factors of x. And we end up in exactly the reciprocal kind of situation we had as opposed to the first case. In the first case, the numerator was constant and the denominator kept growing. But in this case, the denominator is constant and the top will keep getting bigger and bigger and bigger. So, for example, if x was equal to 10, we would have 5 times 10 over 3 is 50 over 3. If x was 1,000, a much larger value, we would have 5 times 1,000 over 3, or 5,000 over 3. So we can see how the denominator remains the same while the numerator is growing very, very much larger, resulting in a larger value of the fraction. The idea is then that this will approach either positive or negative infinity depending on the degree of this term, the coefficient, lead coefficient test. But the idea is then that we don't have a horizontal asymptote. A horizontal asymptote is supposed to have the thing settle out at a specific value, a finite value. This isn't doing that. Now, that being said, when the degree of the numerator is larger, you do get some other interesting things happening. Something to keep in mind is that rational functions are inherently a division. Now, what makes this situation different from the other two is that we can actually divide this. I mean, technically we can divide when the degrees of the top and bottom are equal, although in that case it almost seems silly, but when the degree of the top is larger, well, remember the rule for division. You can divide the big number by the small number, well, easily anyway, and the other way around ends up leading into decimals and stuff, which with polynomials is a totally different story. But as far as division goes, you're supposed to do big divided by small. Works out perfectly. We could actually divide them. it would get a little messy because of the fraction. They don't divide nicely, but it can be done. And that leads us into other things that might happen towards the extreme ends of the function. So many times rational functions will flatten out, like we see in the basic rational function. It flattens out, towards the middle it's doing that vertical asymptote thing, but towards the edges it flattens out at the x-axis. Other functions flatten out in different places depending on the nature of the function. Even just taking the basic function and shifting it would cause its horizontal asymptote to move up or down with a vertical shift. So asymptotes can occur in any, horizontal asymptote can occur at any y value depending upon the nature of the function, specifically looking at the comparison of their degrees. However, when the degree of the numerator is larger, we start getting into some other interesting things in end behavior, and that is upcoming in the next part of the PowerPoint.